Now that we know how to construct a paired t-interval by hand using the calculator, we want to make sure that we can also analyze results that are involving that same type of problem. So we have the U.S. Census Bureau publishes information on the ages of married couples. Suppose we want to determine whether in the U.S. the mean age of married men differs from the mean age of their wives. A random sample of married couples is taken and their age is recorded. And then you can see I have the output in two different computer programs. Not that you'd ever get both computer programs in an exam situation, but you need to be able to read either one of these programs and know what they're giving you in order to be able to analyze it for the questions later. All right, so now the first thing that we need to do is figure out whether the requirements needed to construct the confidence interval were met. And the thing about the requirements for a confidence interval is that they're the same for making the test. So if you're creating either a confidence interval or hypothesis test for matched pairs for the means, all right, so two means matched pairs, then these are the requirements for either the test or the interval. Namely, you need a simple random sample of size n. You need the sample to have no outliers and come from a population that is normally distributed. And you need little n to be less than or equal to 0.05 capital N. So your sample size to be less than 5% of your population size. All right, so let's see here. First thing, do we have, let's see, simple random sample, so an SRS? The answer to that is absolutely yes, we do. It was given to us in the setup because it says that it's a random sample up in the instructions for the problem. So let me put this in 1 second. So right here, when it says random sample, that was given right there. So that's where we have our first smiley face from. And remember, we need 3 smiley faces, 3 yeses in order to be able to move on. So the next thing we need to know is n greater than 30 or is the data set normal? So let me put that in here. And then let's see here. Well, we don't have greater than 30. You can tell that because the degrees of freedom is only 9. So we better have that it's normally distributed. If you look at this normal probability plot here, you don't see the boundary lines like you're used to seeing from Minitab. StatCrunch doesn't make those boundary lines. However, you can tell that the distribution of the dots is normal. So that's a second yes. There, right? So we have our second yes. The graph shows, since the points are linear, that this distribution is normal. Then the last thing we need is that we need little n to be less than or equal to 0.05 capital N. And we're just going to wave our hands at it a little bit because we're talking about husbands and wives. And of course, we only have n equal to 10, and that would be far less than 5% of all the husbands and wives on the planet. So we're kind of waving our hands at it like a magician, but it's true, right? Of course, we have less than 5% of all the husbands and wives, all the married couples in the world, or even in the U.S. I think this was the U.S. because we were talking about the U.S. Census Bureau. So even if it's just the U.S., it's still well less than 5% of all the married couples, right? Because it's talking about the U.S. All right, now we already computed the sample size, so hopefully that didn't throw anybody right there. But since your degrees of freedom is 9, that means that your sample size must be 10. Because, of course, 10 minus 1 will get you 9 for degrees of freedom. All right, now your level of significance is your alpha, right? So you need to look at your confidence level and figure out, let's see, alpha is 0.05 because your confidence level is 95%. So let me type that up. And there we have it. So if our confidence level is 95%, 0.95, then alpha is 1 minus that, right, 0.05. If you like, you could say alpha equals 1 minus 0.95, right? Which means that alpha is equal to 0.05. Just put that arrow in there. All right, we're done with that. Now we need to compute the critical t values, right? T alpha over 2. Okay, so I drew a t curve with degrees of freedom 9. And then to find the critical t values, you're going to need alpha over 2. So your first mission in life is to find that, which is alpha over 2, which would be 0.025. And then remember that your degrees of freedom is equal to 9. Okay, so once we know those two pieces of information, that will help us figure out what our t values are. So we can find the t value with the table or with the calculator, either one. All right, so I just typed that up here. So the 0.025 is the column of your t-table, and then the degrees of freedom is the row of your t-table. So let me grab the table for you to see here. So if we look at the 0.025 column and we go to 9 for our degrees of freedom, you can see it's 2.262 right there. Or you could use a calculator. So let me grab the calculator. And go to distributions, which is above your variable button. Hit number 4, inverse t, 0.025, enter, 9, enter on paste, and press enter again. And you get negative 2.262. So one way or another, you have the value of 2.262, just like Minitab said it was, 2.262. Now, technically, they only want the positive one because they're asking for t alpha over 2. T alpha over 2 is the positive value. So 2.262. All right, so we found the critical t value, which is a kind of a review question from chapter 9 and 10, actually. Now we need to compute SD. SD. All right, so let's look at what information was given to us. If we look at both of these information sets, they're both giving us the standard error of the mean. See it right there? That standard error of the mean is your standard error of x bar. And we learned in section 8.1 that there's a formula for x bar. So let me go type that up. Okay, so in section 8.1, we learned that the standard error of x bar is basically, it's sigma over the square root of n, but we don't have sigma, so we'll have to use s and because it's an approximation, excuse me. So we're going to use standard error of d bar is approximately the standard deviation divided by the square root of n. But we know that the standard error is 1.57 because it was given to us in the problem up in the computer outputs. And we're looking for SD, so we don't know what that is. But we do know that it's the square root of 10 for the denominator because we know that n is 10. So all you have to do is multiply both sides by the square root of 10. And of course, if you do it to the left, you have to do it to the right to keep everything fair and balanced. All right, so let's see here. Oop, I messed that up. There we go, times 1.57. So I'm going to grab my calculator and make it do that for me. So I want the square root of 10, so square root of 10. Then when I use my arrow, I want to get out of that square root symbol. So see how the cursor is still under the square root? So I'm going to press the right arrow button to get out of there. And then I'm going to times it by 1.57. And I'm just going to double check that 1.57 value real quickly, just to make sure. Yep, 1.57. That's what it says right here in StatCrunch and right here in Minitab. So I'll use the 1.57, enter, and I get about 4.965. So there we have it. Right here. S is about 4.965. We have now computed standard deviation. Right? And again, that formula is from the central limit theorem. You know, I'll type that up real quickly. It's coming from the central limit theorem in section 8.1. There we go. So that's where that formula for the standard deviation is coming from. All right, now we need to compute a point estimate for the difference, the average difference, at least we think, for this data set. So you'll remember that in chapter 9, we learned that the point estimate is actually the center of the interval, right? So we need to find that center of that interval. So let me go back here. So if we look at our lower and our upper right there, that if we take the two of them and add them up and divide by 2, we'll find the center. Or similarly here, 0.04 and 7.16. So if we add those two up and divide by 2, we should find the center of the interval. And that'll be your mean right here that I've blocked off for you that you don't get to see, or your sample difference right there. That'll be your D bar. So I've left both of them blank on purpose. I mean like that. Okay, so let me find this. There we go. So we take the point estimate to be the center of the interval, which is D bar. That's 0.0439 plus 7.1561 divided by 2. So you could take 0.0439 plus 7.1561, close your parentheses, divide by 2, and you'll get 3.6. Just another side note, if you'll recall from the inferential statistics sheet, that first page that has the confidence interval parts, right here, you can see right there in that formula, d bar is the center of this interval. So you add on and subtract away your margin of error, which is this back part, to make that interval. So all this is the margin of error, and here's the center. That's the way all the confidence intervals work, except for these ones for standard deviation and variance. Okay, so we know that now. So now we have to remind ourselves of the relationship between the margin of error and the width. So just a little reminder, margin of error, I guess I can erase the, margin of error is half the width of the interval, right? So you have from the edges to the center, that would be your margin of error. So if we want to compute our margin of error from the confidence interval, what we want to do is take the higher minus the lower and divide it by 2. So take half the width of the interval. And I've even drawn a little picture for you. Just put this in here. There we go. And that error is the distance from the D bar in the center out to that upper edge, or from the lower up to the D bar. There, and I just kind of drew in the errors for you. You've got one on the right, one on the left. They're the same size, whatever they are, right? So the error is from the edge to that center. And so the way you find that is find the width, which is 7.1561, take away 0.0439, and divide that by 2. So if we take what we just did, you can actually do it all at once. You can say parentheses 7.1561, take away 0.0439, close your parentheses, divided by 2, enter. And you'll get 3.5561, just like we said it was. Right there. All right, now, does this confidence interval suggest that there is a significant difference? That's interesting words to use. Significant difference between the ages of husbands and wives. So let me highlight that for us all to look at. So significant difference, if you remember from chapter 10, when we started talking about significance, what we're saying is if it's the opposite of the null hypothesis. The null hypothesis is if there was no difference. And if there was no difference, then 0 would be in the interval, because the null hypothesis value in this chapter is always 0. Right? If there's no difference between the two groups, then when you subtract them, here, if husbands and wives are the same, then when you subtract them, you would have the same value. So 5, or well, let's see, these are married couples. So how about 25 take away 25? That should be 0, right? They'd be the same age. So the null hypothesis is that they're equal to 0 when you subtract, that the difference is equal to 0. Well, 0 is not in your confidence interval. 0 is just a little bit outside your confidence interval. Your confidence interval ends at 0.04. Since our confidence interval does not contain zeros, this implies that there is a significant difference in the ages between wives and their husbands, or husbands and their wives, either way. Okay. Again, the null hypothesis value is 0 because that would assume that there's no difference in the age. So if 0 was in the interval, then you'd say, yeah, there seems to be no difference in their age. But since 0 is not in the interval, that implies that there is a significant difference. In other words, you would reject H naught. That's what significant difference means. Sorry, I have to put this in this way. There we go. Okay. When they ask about that significant difference part, that's what they're asking about in code. They're basically saying, can you reject H naught? And since H naught is 0, you can reject it because 0 is not in that interval. All right, now a little review of chapter 9. It's been a while. If our sample size increased, but all other values were left the same, how would that affect the margin of error? So let's look at a couple things here. Let's remind ourselves of the formula. Sorry, I'm trying to pull this up. Formula for these confidence intervals, which is right here. Let me grab that. That's the formula for the confidence interval that we're looking at. And the error part is the back end of that, the T alpha over 2 SD over the square root of n. So let me type that up. There we have it. So since your confidence interval formula is the D bar plus or minus T alpha over 2 times SD over the square root of n, the margin of error itself is the back part of that formula. If n was increased, if your sample size was increased, it would cause the denominator to go to be increased. And when your denominator is increased, it causes the overall thing to go smaller. So if n was increased, it would cause the error to decrease e, since n is in the denominator. In other words, if you ask more people, you're able to make your interval narrower, less error, more accurate.